Hi everyone, welcome back for the second half of 6.1. So I'm going to say 6.1 part 2. We are going to carry on with trig. We're going to do radian, measure, and conversion. So, when I talk about radians, I mentioned this in the last video, what you're used to measuring angles with is degrees. We're used to talking in degrees, and that's what you're most familiar with, but today you're going to learn a new unit of measure, and that's a radian. So, okay, let's take a look at... Let's start with this. We know that 360 degrees is equal to 2 pi radians. So then let's draw it on a unit circle so we can look at that. If we go all the way around like we talked about last day, we know that that's 360 degrees. But we also could call that 2 pi. Or if we went halfway through 180 degrees, so if I went from here to here, then that would be, like I said, 180 degrees. Or we could call that pi radians. So it's just a matter of us adapting or shifting our perspective to look at something that we're familiar with from a new place, a new perspective. But it's still the same thing that's happening, so don't let that throw you off. So if we want to take a look at what this ends up looking like, let me get rid of that. We also can talk about something that's called arc length to refer to this as well. So we talked about this, we talked about this. Let's talk about arc length. So just to remind you, if I go to my starting point here, and let's say I travel around the circumference of the circle, not all the way around. We know circumference is just like the perimeter going around the outside. And we just go a little bit there. We just take a little chunk of the outside of the circle. This could be, let's make this thinner so it's easier to write, arc length equals 1. I just randomly took a little chunk and that's what we're saying. So let's say a portion of it would be an arc length that is equal to 1. So that would mean that we have 1 radian. If we are talking about 2 pi radians, that would be an arc length of 2 pi to help you to put things into perspective. So it's if we go all the way around the circle, that would be 2 pi radians, and that's us saying that the arc length of that is 2 pi. And let's say instead we switch it up, and instead of just a little chunk, or instead of going all the way around, I start here and I take this arc length. Let's think our way through this. So it's just the part that I have sort of written or gone over in blue there. So, sorry, let me make this. Arc length of 1 is when I did it in purple, and arc length when we did this in blue. Well, let's think our way through. If all the way around is 2 pi, and halfway through is pi, what would be the best way for us to give this little portion at the top, which is 90 degrees? Well, we talk about and deal with radians in terms of fractions. So we would say that that is the place where it's pi over 2 radians. And on and on. So we could go, like if we went on to pi, do you see that that would be like 1 pi over 2? Then pi is the same thing as 2 pi over 2. And if I got to the bottom here, it would be like saying 3 pi over 2. And if I went all the way to here, 2 pi is the same thing as 4 pi over 2. So we need to shift our thinking to fractions. And I know even in grade 12 that throws a lot of people off. So I will build in some review. I mean, you should probably know your fractions by now, but I get that maybe they scare you. So we're going to review them a little bit. And maybe they don't, and you can just ignore what I'm saying then. But this little part that I put in the sparkly box, so this box right here, is really important for us to be able to do our conversions, because just like switching from logarithms to exponents and vice versa, we need to be comfortable with switching from degrees to radians. So, an easy way to do that, or a quick example of what this looks like or what this means, is if we are converting, well, that doesn't look like it's converting, degrees to radians. Converting degrees to radians. We want to take our example of whatever we have in degrees, and we want to multiply those degrees by pi over 180. And a good way to think of this is that you want to divide by the degrees to get rid of the degrees, so that in the end you're just left with this pi at the top, because pi is often a part of our units when we're looking at radians. Reminder though, pi is not a unit. I shouldn't have said that. Pi is actually a number. Remember, it's approximately 3.14, but you'll often see your radians given as like pi over 2 radians, or 3 pi over 4 radians, or 5 pi radians. So you never have degrees in your answer if we're talking about radians. So just think, we would multiply by pi over 180 to get rid of the degrees, because the degrees would cancel top to bottom. So then let's look at the opposite, which would be converting radians. This is the short form for radians to degrees. You probably intuitively kind of know this. We're going to take our radians, so we multiply our radians that we would be starting with, like how I said maybe we're starting with pi over 2, and we would multiply them by 180 over pi. And this time you can think of it in the opposite way. We want to multiply by 180 over pi because we want to cancel the pi's out top and bottom, because in the end, if we're talking about degrees, we don't want any pi's in the answer. We would just want a whole number, ideally. Okay, so hopefully that is making sense so far. There's only one way to find out, and that is by doing an example. So what I'm going to suggest is to pause the video once I write out these examples and try them on your own, just by simply, you just need to play around with this really. So I want to make sure that you get comfortable with this. Convert to degree or radian mode the following examples. So you can refer back to those notes if you need to. So for A, we're going to say theta is 170 degrees. We want that in terms of radians. We'll say B is, well, let me do this. B is theta equals negative 12 pi over 11. And for C, theta equals 2.13. And I'm going to sort of talk about what that means, because there's a few different things going on. So this would be a good time for you to pause and work your way through this, and then we will, hit play again, and I'll go through the solution with you. So for this first one, we are wanting to get rid of the degrees. So this is where we are going to do 170 degrees, take what we start with, and we simply multiply by pi over 180 degrees. Okay, so you'll see the reason why we did this. If you have degrees at the top and bottom, those are going to be gone. And if we have a 0 at the top and bottom, those are going to be gone. And although you can give your answer a number of different ways, we'll talk about that. This ends up being 17 pi over 18. This is what I would call exact value form. We've talked about this before, but repetition and review is good. Exact value form, you can hear it in the name. It's with accuracy and precision. So we don't want to round things off. We don't want to divide it to get a decimal. We check to see if we can simplify these numbers top and bottom, but we can't. So we would leave it as this. The other way that you could write that is we could write it with a squiggly equal to sign because we know it's approximately equal to, not precisely. And when you punch that into your calculator, it's around 2.97 radians. So this, we've talked about this before, is approximate form. In most cases, it's beneficial for us to leave things in exact value form. But it depends. If you're doing a word problem and the numbers actually work out to something, like a distance or something, then we probably don't want to use fractions. So use your judgment in each scenario. But for now, I would say this is probably the preferred response. Okay, so moving on to part B, we have negative 12 pi over 11. And so this time, I'll do it in a different color so we don't get them mixed up or they don't run into each other. Negative 12 pi, I feel like that is not the best choice. Negative 12 pi over 11. And what we are wanting to do is to convert this into degrees. So I know that I'm starting with radians because I have that pi there and I don't have the degree symbol. So notice the things to watch for. That's how I know that this time I'm kind of doing the opposite of what I did here. And so this time I'm multiplying by 180 degrees over pi. This makes sense in my mind because the whole reason we did this is to get rid of the pi. And then we can go and simplify this as much as possible. Now, when we are dealing with degrees, it would be acceptable. We wouldn't give our degrees in fractions, so we would want to punch this into our calculators, and when you do that, you would find it's approximately negative 196.4 degrees, and this is how we would give our response or our answer for that. And I like that we did this because I want you to take a look at what this is saying. So negative 12 pi over 11, so you can start to wrap your head around like how many degrees that is. It's negative 196.4 degrees, so I want you to start to think of, and maybe even take the step to do this, where would that fall on the unit circle? Which quadrant would it be in? What would it look like? So maybe draw it out so that you can practice that and tie it in with what we did in the last video. Okay, so for this one, if theta equals 2.13, this is given to us in decimal. Oh gosh, I'm having troubles writing things. Decimal, and I just realized you probably can't see that. This is decimal radians. So this is already an approximate value form. We still need to change that into degrees. So that's the first thing. I don't see a little degree symbol, so I'm going to assume that this is radians. So what I multiply by is going to be the same as in the last example. I'm going to do 2.13, multiply it by 180 degrees over pi, and I started with a approximate value, so I can take that, punch it in, and then round it, and I would get it's approximately 122 degrees when I punch it in. Okay, so I hope you found that helpful, and we're going to do one last concept before we call it quits. That concept is arc length. I mean, I already introduced you to this, but let's take a look at a specific example. Again, if we have a circle, in the center is it's the center, and if I draw these two lines, obviously that's the radius and that's the radius. This angle that's formed on the inside, I'm going to put a theta there. That is going to be my central angle. So that is theta. This part here, well, actually I'll draw this. So R is my radius. That makes sense and looks fairly obvious, I would say. And then this little chunk that's created on the outside, like a little slice of pizza, but we would only, so basically if it's a pizza, it's just the crust, to put this into perspective. So that we call, or we give it this variable S, and that is arc length, which is what our title is for this portion. And we have a formula here. S, let me do that here. S is equal to R times theta. This is important, so important that it goes in a box and gets a little star with it. And so we want to use this to basically do some examples. So here's the first example. Determine the arc length. The arc length BP. So you'll see these variables or letters used to symbolize parts of the circle, and let's say you were given this diagram, we're given a circle on here, and we'll say the starting point is going to be B, and then there's some other point on here, point P, and it goes a little something like this. I know that this angle in here is 30 degrees, we were given that, and maybe I'm going to get rid of the formula because I'm going to assume that you have it in your notes there. And this length here would be 2 centimeters. So that's going to be our radius. So I can just write it again. S equals R times theta. Here's the trick though. In order to use this formula, we need to convert our 30 degrees into radians. This is important, so I'm putting a bunch of exclamation marks there. To use this formula, we need our theta. Maybe I should go back and write it here. That needs to be in radians. If it's not in radians, we better change it to make it in radians. So that would be the first step. So remember what we just finished learning. 30 degrees times, I want you to get into this habit. Know that if I'm converting into radians, I know the degrees go at the bottom because I'm wanting them to cancel. So pi must be at the top. So it takes the memorization out. We're done and you already know this. The degrees would be gone. That's why we did this. The zeros would be gone. That's why we did this. And when we work our way through this, and we simplify this, we get that this is just pi over 6 radians. Therefore, S equals the 2 that we started with, the 2 centimeters, times pi over 6. And so when we convert all of this, we get pi over 3, which is approximately 1.05 when we punch it into our calculator. And the reason we did that is because it's an actual length or a distance, and we know that the unit is centimeters. So it would be 1.05 centimeters if the radius was given to us in centimeters. So you know that we keep our units consistent. Okay, on to the next example, and this is the last one. Find the distance traveled by the tip of the second hand on a watch of radius 16 millimeters as it moves from the 0 0-second mark to the 40-second mark. I think the hardest part about this was writing all that. So, this would be a good time for you to pause, soak that in. I find it's often helpful to draw a diagram when you're figuring out something like this, so take the time to do that, and then when you're ready, hit play again. You know me, I can't get through a video without drinking tea. So, let's sketch out what this looks like. I guess, what am I doing? We don't need that. Let's draw what the face of the watch would look like. So, if we're drawing this out, this would be like the 60-second mark, right? This would be 16 because we were told that the second hand on a watch of radius 16, so that must be this. So that makes sense so far. And then we know how a watch goes. This would be 15, this would be the 30-second mark, this would be 45. So just to sort of wrap our head around what's going on. So, do you see that to go from 0 to 40, it would be, so 0 to 40 seconds is 40 out of 60, which is 2/3 of a revolution. So, you'll notice this with a lot of our trig stuff, like we're thinking in terms of fractions, like we're trying to see what portion of the circle of a full rotation would be covered, which is 40 out of a total of 60. Okay, so that makes sense. Therefore, our theta is 2/3 of a revolution, and a full revolution, when we're thinking of radians, is 2 pi. If we were thinking degrees, it would be 360 times 2/3, but we're doing radians because we know we need to talk about arc length. We're looking for the distance traveled, that's arc length. Right? So that's the first step. We wanted to figure this out. This is like saying over 1, so obviously we have 4 pi over 3 when we multiply 2 over 3 times 2 pi. So we just figured out what our theta is. It's this many radians, so that's going to help us. And in fact, I'm getting rid of the other box because we don't really need that. And we know our formula. S equals R times theta. So our R we already talked about was 16 millimeters, and our theta we just got is 4 pi over 3. And when we work our way through this, basically it's just 16 times 4, so it's 64 pi over 3. And we don't ever, like, it's that many millimeters. We're not going to give millimeters with pi and fractions and all of this, so it makes sense in this situation to convert this and round it, and it would be around 67 millimeters. So after all of that, this would be our solution. We always want to go back and check. It says find the distance traveled by the tip of the second hand. So the distance traveled by the tip of the second hand on the watch would be 67 millimeters. So you're doing page 255, numbers 3 and 5 to 7. For all of these, you can just do odd letters. So remember, that means like A, C, E, etc., etc. And 8 to 16, you can do all of them. I think you'll find this is manageable. And I hope that you found this video helpful.